Hello, everybody. Welcome to the third lecture on Theory of Open Systems. We are still in the middle of closed systems, actually, but we are chugging along a bit. So I kind of said what I wanted to say about time ordering and unitary evolution operators, except for one more thing, something I'm calling computability of unitary evolution operators, because we investigated, analyzed some math, right? But when push comes to shove, you would, from time to time, you actually have to calculate something, right? To get some testable predictions in the end. So we had our formulas, our equations for unitary evolution operators, but what about computing them actually to get some numbers? Well, there are like a couple of things to say about that. So the first thing is computability is kind of easy if Hamiltonian is constant. Okay, so no time ordering needed then. We can just calculate evolution operator by taking exponent of h, which is given by the series minus I t power k, and just take h power k. Okay, so we had an example with two-level systems, well, Hamiltonian given by sigma operators that you can actually calculate this like analytically. So we just do the series can be calculated, but that's a special case. Okay? That's usually doesn't work like that, but still there is a way. If Hamiltonian is constant, right, it's a Hermitian operator, it means that it can be diagonalized. Okay. What diagonalization means that Hamiltonian diagonalize Hamiltonian. Jesus. Let me write it again because it's so ugly. Diagonalize the Hamiltonian. So it means that you can find a basis of eigenstates of your Hamiltonian. Let's call this basis D. And such that, n is just some indices, 1, 2, whatever, however we wish to label them. And those kets are such that when Hamiltonian acts on such ket, you get a number, which I will write with small h, okay, of n times n, right? That's the definition of eigenvector and eigenvalue of Hamiltonian. Or to put it differently, the operator of the Hamiltonian can be spectrally decomposed, which means that you can write it using the basis as a sum of projection operators onto eigenkets times weighted by the eigenvalues. Okay, so when you have this form, it's very easy to calculate any function of operator. So in particular exponent, so if we plop this spectral decomposition here into our series, you can easily see what's going on. Identity plus k 1 to infinity minus it k factorial. And let's start. So we will have n1, hn1, n1, n1. So that would be the first Hamiltonian, kth Hamiltonian, kth power, h and k, nk, nk. I just substituted spectral decomposition for each Hamiltonian. But now obviously the sums can be gathered together. So let's take a huge sum over all the n's. Nk, we have all the eigenvalues. Nk, and then we have projectors, which are, one goes to the other. So we have like this, and this acts on n2, n2, and so on, nk, nk, right? But these are orthogonal states, right? Eigen vectors of Hermitian operator are orthogonal, they form bases, right? So this guy is just delta n1 and 2, okay? Right? And here it will attack. So let me write what's here. We will have n3 and 3, right? And they will meet together, and another delta, n2 and 3, and so on. All the projectors will eat each other up, and you will end up, and once they multiply with each other, they will essentially synchronize their indices. With factorial, there will be n k. So we will be left with ket from the very left side. We'll be left with ket from the very right side, this guy, and the rest will just turn into deltas. 1 and 2, and 2 and 3, delta and k minus 1 and k, okay? And this is fairly easy to, deltas are easy to handle with sums, right? So what it tells us that all the n's will be the same, and we'll be left with only one n at the end. Let me check if I'm recording. I am recording. Good, good, good. Okay, factorial. So there will be n, let's say n1 left, hn. So all the n's are the same, so this will turn into h of n1 to power k, n1, n1. Okay? So now you take the sum over n outside the sum over k. Well, you don't really need to, we can just label it with n. The n1 is just spurious here. Mm-hmm. From 1 to infinity, k, k factorial. So we will be left with ket from the very left side, this guy, and the rest will just turn into deltas. 1 and 2, and 3, delta and k minus 1 and k. Okay? And this is fairly easy to, we can just label it with n. The n1 is just spurious here. Mm-hmm. From 1 to infinity, k factorial. H of n.
Do it for those series. Change to sums.
Yeah, I can move sum over n in front of sum over k.
Yeah, but it's like it's infinite, so sum. So can we do it?
Yes.
Okay.
Yes, you can. Everything is bounded. Okay, the dimensions are finite. Let's say everything's fine. Don't worry about it. And you know, so all this stuff can be just, you know, this series here is basically a series for exponent, but of a number now, okay, of the eigenvalue. So you can just, you know, take everything in and just write it as AIT H of n on n, okay? Or in matrix notation, right? Because we have our basis, we have our Hamiltonian in our basis, right? If we write it as a matrix, would be H1, H2, H3, and so on. So that would be a matrix representation of our Hamiltonian in the basis D. So if you take exponent ITH, so this is like taking the exponent minus IT of the diagonal matrix. And of course, everywhere else are zeros, right? Only entries on the diagonal. It just turns into a matrix, a diagonal matrix where you have minus I H1, E I T H2, and so on. And this kind of trick or computation works for any analytical function of operator. Okay, if you have some function f of h, okay, a function that you can express as a series, as a Taylor series, so analytical function, and then you can always write it as f of h1, f h2, blah 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 blah, in the basis of eigenstates of the operator. This is a general rule that's yeah, generally okay. I won't say more about mathematics of it. There is a lot to say, but this is where we stop. So if you have your Hamiltonian is constant and you can diagonalize it, it's seemingly the problem of computation of the evolution operator is kind of trivial. Okay, it's just if you can diagonalize your Hamiltonian, you can easily compute the function of it. But there are like two things to bear in mind here. First one is that you know, sometimes, although diagonalization seems to be really easy, but sometimes it might be unfeasible for technical reasons because let's say your Hilbert space is just too big, your dimension is too big, your matrix is too big, your Hamiltonian is huge, and even numerically diagonalizing it numerically might be like some instabilities, something is difficult. Or to make matters worse, if your Hamiltonian is not constant, is actually time dependent. So if you have h of t, okay, the method with diagonalization doesn't work because you cannot find a one basis in which all Hamiltonian at each point in time is diagonal, okay? Because if you could find such a basis, that would mean that your Hamiltonian at different points in time just commutes with itself. okay? If you could find such a basis, that would be equivalent to saying that Hamiltonian commutes with itself, and then it's essentially a constant Hamiltonian, if you remember. You don't need time ordering, for example. Right? So if your Hamiltonian depends on time, diagonalization doesn't work. And what then? How do you compute your goddamn unitary evolution operator if you cannot rely on this formula? Well,
you find changing frame preference.
Well, that would essentially amount to computing the time ordered exponent. Okay, if you just go step from step, that's if you cannot find one basis, right? It's no longer easy. Okay, but we still have our we know what our time ordered exponent is, right? So we have our I. STHU du. Okay, if it's no longer constant, we have our series representation, right? Which is the thing that we can rely on always. S to T du K, time ordered integrals d1, and we have our Hamiltonians K H U1. Okay, so one idea would be to, all right, so maybe we can do some approximations here. Okay, perhaps it would be a good idea to basically cut this series on some finite order. Okay, then you have a finite number of integrals. You have integrals of products of Hamiltonians, which and you have to execute it for finite number of terms. So that's something that in principle could be computed numerically, numerical integrations, or maybe by hand if you are patient enough. But as it turns out, this kind of approximation, where you take this time ordered series and you cut it at some finite order, they are pretty bad. Those are pretty bad approximations. Okay, if T is close to S, so you have short time interval, then very short time interval, then like cutting at K0 equal to 1 or 2 or 3 might be a kind of good idea. You won't make a lot of mistakes by doing that. You won't accrue a lot of errors by doing that, and it might work. But aside from that, if you want to have your evolution over a longer period of time, it's just completely, this approximation is just very, very bad. And one argument why it's bad, this evolution operator is unitary, right? But now you take this whole, so this means that this whole series, when you sum everything up, is unitary operator. But if you cut it on some finite order, it's definitely not unitary immediately, okay? So you will have some, rather than behaviors like, kind of like oscillations, you will get something that, and just explodes somewhere to infinity, right? So cutting your series in this way is just asking for this kind of trouble. So it's like with cosine or sine. If you want to compute cosine or sine with Taylor series expansion, right? And you want to keep only finite number of terms, you probably saw that, well, in the beginning, it's kind of okay. You are capturing this band, a first band, for example, but then you just completely lose this oscillatory behavior. And unitary operators are kind of like, they are like oscillations, basically. So this is a bad idea to use this particular kind of approximation, except for the case when your time is very short. Okay, then things might be okay. So if not that, then if not this kind of thing, then what else can we do? Where typically you resort to some iterative numerical methods at this kind of problem. So like in many branches of physics, you basically try to rely on some kind of differential equation and you want to integrate it numerically, right? Newton's equation in classical mechanics or Hamilton equations in classical mechanics. And in quantum mechanics, it's, of course, we also have our dynamical equation, Schrödinger equation for cats, or a dynamical equation for evolution operators, right? So if your Hamiltonian is not constant or diagonalization is unfeasible for technical reasons, you have to resort to numerical integrations of your dynamical equation. Okay, with some initial condition, let's say SS is 1. All right. And this leads us to a assignment. So I would like to ask you to write a code to actually numerically integrate a dynamical equation. So it's assignment number 12, okay, in the script. And you have here some, for two-level system, a Hamiltonian is defined here. You have your dynamical equation with some parameters, and I would like you to try out 3 methods, numerical integrations, because you're aware there are many ways to do it actually. So we have Euler methods, Runge-Kutta method, and Crank-Nicolson. If you go to what those methods are, I mean, if you pop to the solutions, they are like succinctly summarized here. Okay, so you can check out what you have to do actually in your code and try it out. Okay, try out writing your code and don't cheat. Okay, I mean, I know Python has like libraries where Runge-Kutta is implemented, everything is implemented. I tried, from it would be a simple code anyway. It just needs to multiply some matrices, right, and insert a loop. Okay, try it out just to have a feeling for it. And well, you can also compare it to series. Although that would be the cutting of the series, but that would be more involved. But try out writing some code just to see how it feels. So to summarize this, so we have our theory of maths behind the evolution operators. Practice behind them is most of the time is just integrating a differential equation, and this is easy. Okay, this is easy problem. Even if your dimension is quite large, it's still kind of not very difficult. Okay, if you have enough memory, it's and a couple of minutes to spare, you can compute them quite easily. Sometimes you can do the diagonalization. If Hamiltonian is constant, this might be challenging numerically from time to time. But even if Hamiltonian is constant, okay, and you cannot diagonalize it for some reason, you can still solve the dynamical equation just with constant Hamiltonian. It's no problem. Okay, so calculating, computing unitary evolution operators is therefore easy problem. Let's say easy compared to other problems that we will encounter in a couple of lectures. This is very easy in comparison. I'm not saying that everything is super easy, but it's like compared to everything else, it's kind of easy. All right, so that's a concept of computability. Okay, let's go to the next section, and then we will begin. Then we will make a break for a couple of minutes. So that was computability, important concept in my opinion. But now the next step would be the next tool we will need in our toolbox are density matrices. Density matrices. All right, so previously we talked about quantum systems. They have states, and in standard formulation of quantum mechanics, you assign a state to your system, and those states we represented with cats, and maybe time-dependent cats, right? They satisfy Schrödinger equation. You can represent them as unitary evolution operator acting on initial state, right? This is how they evolve, and so on and so forth. But as it turns out, this is not the only, okay, not all states of quantum systems can be represented with a vector, okay? It turns out you need something more, something that's called density matrices, which are raw density matrix, and it is a linear operator. So a matrix on the space, on our Hilbert space where our cats live, okay? And this operator, it satisfies, it has to satisfy three conditions. So one, it has to be non-negative, raw. It's supposed to be raw, okay? Maybe it's not P. P would be like this, okay? This is raw. Okay, I'm sorry, I don't know how to write it more pretty. Oh, this is raw. So is raw is non-negative or positive semi-definite if you want to be fancy. What it means is that for every cat that you can come up with, so if you take an average value of rho, it has to be a non-negative number, okay? Second thing, rho is Hermitian. It's Hermitian. So if you take a dagger to rho, rho is reproduced, which tells us that its eigenvalues are real numbers. Non-negativity tells us that those numbers are real and non-negative as well. So it's like spectrum of rho is always made out of positive numbers. And fun fact, non-negativity actually implies hermicity automatically. So this is a spurious condition. And why is that? Because positive semi-definite operators can always be written in the following form. Okay, you can always decompose them like that. This operator O, you can think of it as a square root of rho. Okay, and this guy is, if you have this form, it's clear that it's Hermitian, right? If I take a dagger to that, so I have to swap the positions, right? And apply dagger. 2 daggers equals no daggers, so you just go back to the same form, right? So hermicity is already implied by non-negativity, although not the other way around, of course. And the third point row has unit trace. Unit trace. Trace, which means that you take trace of row and it's equal to 1, a number 1. Okay, so when you combine all this stuff, you have an operator that has only non-negative eigenvalues that actually sum up to identity. So it's like probability distribution, right? Eigenvalues of density matrix can be thought of as a probability distribution. And now the simplest example of state represented by density matrix are so-called pure states. Pure states. You get a pure state when your row can be written as a projector on some ket. Okay. And this, if your row is pure, then this is how it corresponds to the state kets we started with. Okay, when row can be always written like this, you can basically reduce everything to the description using state kets. Okay, but those are the simplest kind, the pure states, because you also have mixed states. Mixed states. Those are, I always forget, convex or concave? Convex. Mixed states are mixtures or convex combinations of pure states. So in human language, this means that row can be written as sum over some index I, and you have Pi, coefficient, and projection on some ket psi I. Okay, where it's a convex combination, which means that PIs are non-negative and they sum up to identity. PI sum up to 1. So like a probability distribution almost. And those kets we are projecting is just some collection of, it's just some collection of kets. It can be arbitrary, whatever. Okay. So those guys mix states. Well, I won't go into details, but if you want to verify if those formulas actually adhere to those requirements, it's very straightforward to check. Nothing to see here. Not very interesting. But about mixed states, before we try to interpret them, there is a very peculiar but also very important feature about mixed states, because I wrote here this kind of formula, but as it turns out, it's not this mixed states. This representation of mixed states is not unique. Okay, there is a theorem. I wrote it down here. It's a Schrödinger, Hudson, Hozas-Wuters theorem, also known as purification theorem, if you want to check it out in Wikipedia. And it states that any mixed state has a infinite number of representations as convex combinations of projectors, which in human language, by human language I mean inscriptions. So if your row, you can write it like this, right? There's also a representation when you can write it with some pi prime. and some different collection of projectors. And there's like a third option, say bis, CI bis, and you can go to infinity. And each of those guys, so this is like pi prime is also non-negative, and they sum up to 1. And again, this is a collection, some collection of cats. P bis is the same, tris is the same, and so on and so forth. And this is kind of weird, but there's a nice example that you can showcase this feature. So to showcase how it works, so let us consider a density matrix. Consider density matrix that we know that we can actually write it with this as a mixed state. And we have some psi's, and those psi's, let's assume those psi's, psi I, psi j, they are not orthogonal, okay? Which is allowable. It's again, those cats are arbitrary, they can be whatever, okay? As long as pi are non-negative and they sum up to identity, everything is fine. But on the rho is also a Hermitian operator, right? This is always a Hermitian operator. So we can always diagonalize it, right? So we can write down its spectral decomposition. So rho is also equal to sum over n, let's write it, rho n, that would be eigenvalues and eigenvectors n, okay? It's always possible because Hermitian operators. But those, so again, this is because rho is non-negative and trace 1, eigenvalues, so rho of n is always non-negative, and when you sum them up, they add up to identity, as we noted that previously. So this spectral decomposition is actually one of, it's one of those Wouters, Schrödinger, whatever the hell representations, but it's for sure different than the previous one, because here we picked psi's that are not orthogonal to each other, but eigenvectors of density matrix are orthogonal to each other. So n prime. Okay, so this is not just a matter of relabeling cats. This is actually a different decomposition into a mixture. Okay, so this is like a simple example you can always take to show that mixed states have infinitely many, or at least more than one representation in this convex combination of projectors. Okay, this is a thing to bear in mind. And why is it important? Because the fact that those weights here, those pi primes, they are like probability distributions, right? Because they non-negative and they sum up to 1. So it's tempting to assign to it a probabilistic interpretations, to mixed state, assign to mixed state some probabilistic interpretation. Like, for example, let's say we have some apparatus, some machine, some device that prepares our system in some initial state, okay? And this machine, it can like initialize our system in a pure state, so in some cat, but it also has some random component. There's some randomness there where it picks the setting. So if it can initialize in psi I, but which I it picks there's some randomness to it. So when we run our machine, we don't know which setting it it has chosen in this particular run. So to account for this uncertainty, right, we are forced to adopt some kind of probabilistic description, and this is how density matrices come in. We just take a probabilistic combination of those possible initializations by our machine, okay? And that would be a nice interpretation, but this is this decomposition into mixture is not unique, right? So there is some, if really that you have this machine that does initialization in the way I just described, then yeah, for sure you can write down your initial state in this form. That would be okay. But because of this non-uniqueness of this mixture representation, you cannot always say that every density matrix is there because there was some machine that does this stochastic initialization. This you cannot say, okay?
Like the problem with okay, anyway. And it's but I understand that can be interpreted as if you measure in this space, then that would be probably.
I mean, please, if you measure in base, in what base?
Of phi's.
But phi's don't form. This collection is arbitrary, not necessarily orthogonal. This collection doesn't have to be a basis,
And to do orthogonal measurement? No, you cannot.
Yeah, I mean, there are some generalizations, but
Okay. If we take the orthogonal base, then it's to work. And non-orthogonal base, it would not.
I mean, it's look, this probabilistic I mean, when you do measurements on the system that is initialized in a state described by mixed density matrix. Okay, so it's okay to think of it as because even if you have pure state, okay, you still have some probabilistic distribution of results of measurements, right? So this is like typically how people think about it, and I think this is not wrong, is that so you have this like purely quantum mechanical fundamental randomness, which is like encoded in pure states, but you can like layer on top of it like a classical additional randomness that might be like maybe can be interpreted more along the lines of some uncertainty or ignorance of observers, stuff like that. So it's just like layering different kinds of randomness on top of each other. And this kind of interpretation, I don't think it will lead you to some false conclusions about your measurement results. But if you want to, if you would like to infer from that something about the system, the state of the system, how it was, let's say, initialized, this is where things become more dicey, let's say. It's not an easy topic to consider, but all I want to say here is the probabilistic interpretation is very tempting and kind of imposes on us. It imposes itself on us because the coefficients are the coefficients pi behave as probability. There could be a probability distribution, but it's not unique representation. So this has to do something weird. Okay. So sometimes there are cases where it's really the origin of this mixedness is like you can trace it back to some really classical uncertainty, like with this device. But there are other scenarios where you get mixed states, open systems, for example, which we'll talk about, is a scenario where you get mixedness like dynamically, okay? And then you cannot say that there's some machine that does it. It's like completely different effect. So, you know, it's just it's a interesting topic, and I don't think we can like go into all the details right now about it. But just be aware of this, okay? It's not so simple to interpret what this mixed state means, okay? What else? What else to say? Oh, apropos measurements. So, you know, the state on its own, it's like only a even in standard formulation of quantum mechanics, state of its own is just it's a thing. It's not something that you can look at. Okay, you use states to let's say compute some testable predictions, some empirically testable predictions. So one of like standard example is an expectation value of some observable, right? So observables, you represent them with Hermitian operators in like standard formulation, and the expectation value, let's write it like that. So this would be observable A represented by some Hermitian operator A. And the rule how to extract this testable prediction is you take your row, you take operator representing observable, you multiply them together and take trace. So this is the rule for calculating expectation values. And in case of pure states, so in case of pure states, so you have, if your row is just a projector, you multiply and you take trace. Well, this reduces simply to average of A, which is like the formula we know from like description using only cats. Okay. So this is this rule. Another rule that will be important for us is how do you you have states represented with density matrices. How do you evolve them in time, right? That's the like key point for us. Well, the rule for time evolution is again it utilizes our good friends. No, let's keep the U. So we have our so we have a system. Dynamics is generated by Hamiltonian. We have our evolution operators, but now states. If you represent state with density matrix, how do you apply this evolution to density matrices? Where the rule is, if you have rho at time t is given by, you can take rho at time s, and you evolve it by sandwiching it with evolution operators. ST. Okay. Or TS, rho S, rho TS. Just a reminder, right? If you take dagger of evolution operator and just flips the direction of time, okay? So this is the rule. And again, for pure states, so for pure states, you would write something like this: Ts psi s, and this you can write as Ts on psi s, but dagger of everything, okay? And this we know what's going on here. This is just a standard evolution of cats. So you would get psi t, psi t. Okay, so again, for pure states, it just reduces to the things we talked about previously. But the new rule is this, okay? And use these guys, we know what they do, we know how to compute them. We discussed that, so this is known thing. The new thing that's going on here is just you have to use two of them, a pair of them, and to evolve the density matrix. And this, okay, and this rule actually, so evolution operators, we know they are like, we have dynamical equation for evolution operators, which are intimately connected with the Schrodinger equation for cats, right? So we have evolution operators, dynamical equation, and now we have this new rule for evolution of density matrix. So is there a Schrodinger equation for density matrices? Yes, there is. It's called von Neumann equation. How do you write Neumann? No, two N's. That's always tricky for me. It's two N's, one N. How do you know? Von Neumann equation. So this is again a Schrodinger equation for density matrices. So we can derive it from the rule, evolution rule, quite easily. So we take rho t. So we have our rule. The time-dependent thing is our use, evolution operators. So we have dt rho s, rho st, plus uts rho s, and this we can write as ts dt as dagger, okay? And we have our favored dynamical equation, so we know what this derivative does. It gives us minus I h of t, and brings back evolution operator ust. And on the other side, we have uts rho s. Here we get minus iht uts, but everything is under the dagger. So we execute the daggers, we collect evolution operators and row into row of t. So we have minus ih of t row t, and here we have plus I row t h of t, but it's on the right side of row, right? Because it's here. When I take a dagger, I just exchange minus I turns into I, so I, not minus I here. H goes to right, U goes to left. H dagger is H, nothing happens to H because it's Hermitian operator. U daggered just changes into U from S to T, but it acts on row S acts on it, so it's, you recreate row of T. but H stays on the right side, which can be written as a minus I and commutator of H of T with rho of T. So this is von Neumann equation. And what else? Okay, it's 11. We can take a break before we go. Sure. Yes, of course. Yes. So let's take 10 minutes break. I think that will be enough. All right. So let's carry on. So we have our von Neumann equation, but if you notice, there's an awkwardness here, because we have our density matrix and we have to sandwich with two operators. Everything is like doubled. It's kind of like not very convenient. So perhaps there is a better way to deal with density matrices, and there is a better way. And this better way is called superoperators. Okay, so what are superoperators? So how do you want to put it? All right, so mathematically speaking, right, the Schrödinger equation, we have it's a differential equation where you differentiate the vector, right? And you get on the right-hand side, you have some operator acting on the vector, right? Because state kets are vectors in the Hilbert space, right? But now, again, mathematically speaking, formally speaking, operators on Hilbert space are also vectors. They also form vector space, right? Because you don't need much to form vector space, because you get vector space if you have operator A and B, and you define their sum. Combination. This is also an operator, right? So this is all you need to have vector space. So operators on our Hilbert space are also from vector space. And sorry? No. That's extra thing. That's normed vector space would be. It's a Banach space, I think. If operators can be seen as vectors, so you can also have operators acting on those vectors, or super operators.
Measurable and closed, I think.
I think Banach is a space plus norm.
Yeah. I mean, because it's closed.
That's like closeness it's about topology, so that's an extra bit.
But Banach feels close. It's not.
It might be like if you have norm, it can be closed or something. But
the normal vector space might actually need to be closed in a way, but adding vectors still goes to vector. Like that's
yeah. Adding, multiplying by scalar, and addition if they are.
So it is closed.
In this, I mean, close. This is a what close means. It's.
I think what close was about an operation on the elements inside the set, usually elements inside the set.
That would be a close. So we would say it's close with respect to addition and multiplication by scalar. Okay, so that's. So it's a field, no, not field, algebra, whatever. The point is that you can treat operators, including density matrix, also as a vector, and you can, so if you have vector, if you think of them as vectors, you can also have operators acting on those vectors. That would be super operators, right? And then if you look at the von Neumann equation from this point of view, so rho of t. So on the right hand side, we know we have H commutator with rho t, right? But if you now, okay, let's think of rho as a vector, and what's happening on the right hand side as a action of some super operators on rho. So that would mean that you would write it like this, okay? So this thing now, this is what would be my super operator. And let me just pick a notation for this. So what's happening here? So this bullet here, the bullet, I will use bullets to denote like a placeholder for the argument of the super operator. So when the super operator acts on operator, on a vector, right? You place the argument in the, I mean, the bullet is a placeholder for the argument. So in other words, if I had, let's say, super operator defined like this, and I act on B, right? So the rule is I just take B and put it into the, I replace bullets with the argument. So I would get a B times B A. Okay, and notice that the order matters because these are operators. So this is operator in a linear operator, even in a sense that it acts on B on operator and produces operators, right? So it's like operator matrix acting on vectors produces vectors, right? And I'm using hats to denote like normal operators, and I will be using this calligraphic font to denote super operators. Okay. So now, why this is like insightful thing to do? Well, you see, Schrodinger equation is a very simple beast. You have time-dependent vector, you differentiate it. On the right-hand side, there is some minus I, some operator or super operator acting on the vector again, right? And this operators plays the role of the generator of the evolution, of the unitary evolution operator you get by solving this equation. But from mathematical point of view, is just you have vector space and you have operators in vector space, and the Schrodinger equation is just operators acting on vectors. So mathematically speaking, von Neumann equation has the same form as Schrodinger equation. It's just you replace different vector spaces. You're using different vector spaces essentially, right? So, and the thing about equation is that the same equations have the same solutions, right? So if von Neumann equation is essentially the same as Schrodinger equation, and we know what is the solution to Schrodinger equations, time ordered X, generated by the operator slash super operator acting on the right-hand side. So we immediately know what's going on with the solutions to von Neumann equation, right? So we would write rho t equals time ordered, and we are ordering the generator, which is this super operator made out of commutator, which is sometimes in the business called adjoint superoperator, I think. And you have exponent minus I S T generator U du and acting on density matrix as time S. All right. And what do I want to say here more? Yeah, okay. And so this guy here, so we recognize here a super version of evolution operator, or unitary evolution super operator, which for short I would just call it unitary map. Okay, and I will denote it calligraph font U from T to S. Okay, so this will be unitary map. Why it's called unitary, we will see soon. And again, it's like with evolution operators, unitary map understood as time-ordered exponent generated by the this Hamiltonian, adjoint Hamiltonian superoperator, but it's ultimately just defined by series. Let me write down what the series is: k to infinity minus I to k. We have integrals S to T du k, time ordering U2 du1 H UK composed with further H's. So what is this mysterious bullet in front? Well, in the language of superoperators, standalone bullet is just identity, right? Right. Because imagine, you have bullet acting on some operator A. Well, this is just A, right? So a neat notational trick for denoting the identity superoperators. So this guy, but we can be more explicit about what's going on here. Maybe let's go to the next page. Plus sum k1 to infinity minus I k, or in favorite integrals. Those guys, so okay, bullet, right? They are like adjoint, so made out of commutator and Hamiltonian operator. But this you can even go further if you want to, if you need to. Let's see if you will be shocked by what I will write here. Okay. K minus 1. HU2. HU1. Bullet. Is it weird for you that it's I can write it as this kind of nested commutator? It's clear why it looks like this?
Saying the third person believe that and just imagine exactly how the calculate that.
So if you want to check out this kind of identities, just act on the like with standard operators, if you have, someone gives you a formula, you want to see what's going on, just act on some vectors. So same here. If you want to see this effect of nesting, so let's just take a H, say U2 bullet composite HU1 bullet. So first two guys, and act on some row. Why not? Let's use row. So what's going on here? So you take let's act with the first guy first. Q2 bullet. So be HU1 commutator with row. Okay. So this is operator, right? It is an operator. It's sum of operators, so it is an operator. So you could write down, just write it down explicitly. So it's HU1 times row minus row times HU1. Okay. And super operators are linear. So we know how to deal with the sum. HU1 row minus HU2 row HU1. Okay. But now commutator is linear, so we can just bring it back together. HU2 HU1 row. All right. And now, where is row? Row is sitting here. So I can rewrite it as a super operator again using bullets. All right. This is how if you have some formula, just act with it on some argument and see what's going on. Just to make sure you understand how it works. So this is why we have this effect of nesting. Right? So this is why you get this nesting. It's very characteristic structure, actually. But there's more, because we have this solution to von Neumann equation in terms of super operators, right? But we also have a rule. We have a rule for evolution of density matrix in terms of evolution operators, not super operators, and they have to be the same, right? So we can immediately find the identity, a very interesting identity. You know what? Let's be explicit here. ST H U du H acting on row S T H E I S T H U du dagger. Okay. And this is true for any row S, any initial row. So this is a super operator identity, actually. So this implies that EISTHU equals TH ISTHU du bullet TH ISTHU du dagger, or in shorthand U equals UTS bullet ST. This is sometimes called Baker Hausdorff Campbell. I think there's fourth name there, identity. Now you can, of course, you can show it algebraically as well if you are inclined to, but you can just use the Schrödinger equation and von Neumann equation and the superoperator notation to also show it. 20 minutes. What else? What else? All right. So now, what are the properties of U? I'm calling it unitary map. So there's probably a reason why this kind of name. And it's so intimately connected to unitary evolution operators. So they must like share some properties for sure, right? And they do. Of course they do. There are some properties are shared. Some properties are shared between calligraphic U and hat U. So for one, since generator H, yeah, there will, yes, there will be, but let me go step by step. But of course, since U is Hermitian, asterisk here. Okay, I am saying this calligraphic H, so this kind of superoperator is Hermitian. But what is Hermicity? Hermicity is always defined with respect to some inner product. Okay, so far we know we can treat operators as vectors. So superoperators are just matrices acting on those vectors. But what is the inner product? Can I make a Hilbert space out of vector space of operators? What would be the inner product? And of course, you can do this. You can endow or equip space of operators with scalar product, and the standard scalar product you would choose is something. How do they call it? Schmidt product? Hilbert-Schmidt product, they call it, but I just call it trace product. So this is how you define your scalar product, okay? So just take a dagger, multiply it with B, and take trace. This gives you a number. You can check that it has all the properties you require from scalar product. This also gives you some kind of norm, trace norm for operators, right? And so on and so forth. But once you have a scalar product, you can now talk about hermicity, right? Because hermicity means that a superoperator is Hermitian if A HUB equals HU AB. Okay, this is how you, when you have inner product, this is how you define hermicity. Okay, it's the same for normal operators with hats. It's the same for super operators, and it's sometimes it's important to remember that it's with respect to inner product you are using in your space. Okay, so to show that H curly H is Hermitian, you just have to do the calculation. So if we start from here, so we would have to H U on A dagger with B. But this is just, it's H U with A, commutator, dagger B. But this is A dagger H U times B, right? Because the products will reverse order, right? And Hamiltonian is Hermitian operator, hat operator. So reversing order amounts to just flipping the commutator, the arguments in commutator. And the dagger A is just some random operator, so it's generic operators, it's not necessarily Hermitian. But now you can use the cyclic property of trace to rearrange stuff to basically move commutator from A to B, from A dagger to B. So you would have here A dagger HU B minus trace HU A dagger B. Okay. Use cyclic property to move H from here to here, and you get trace A dagger HU B minus B HU. Which is A dagger commutator of HUB. This is A HUB. So it's Hermitian. Curly H is indeed Hermitian. But if H is Hermitian, it's a generator of time-ordered exp. This means that time-ordered exp has to be unitary. If you recall how we showed unitarity of evolution operator, which is time-ordered exp generated by Hermitian generator, the Polte properties would just transfer. So this implies that yes, dagger again understood in the sense with respect to the trace inner product. This guy is actually U2 minus 1. And it's also actually also means this. So going further, since unitary map, which we now know why it's unitary, because it is actually unitary. It's a unitary superoperator, that's why unitary map. Since it is the time-ordered exp, it satisfies composition rule. Composition rule. Like it's a time-ordered exp, also a solution to von Neumann equation or to dynamical equation. So it's all connected. Yeah, we have a composition rule, and it's dynamic, and it has its own dynamical equation. Again, because it's a time-ordered exp. So if you take von Neumann equation and just strip it of the density matrix, you get equation for U itself. Just like with Schrödinger equation. With initial condition identity. Okay. Damn, I'm so slow. Like really, really slow. Okay, it also has a set of, you also have set of properties that are not, I mean, U with hat, evolution operator, okay, there are some properties for curly U that U with hat doesn't have because they wouldn't make sense for evolution operator, but for unitary map, they make sense. And those additional properties are additional properties. U preserves trace of density matrix. I mean, it's kind of unitary operators, they preserve norm of vectors. So this is kind of the same thing, but with when norm would be defined as a with trace, I guess. But in more practical sense, so what I mean is that you take your evolution unitary map, act on rho S, you take trace, and you want to see if the trace is the same as the trace of the initial density matrix, which should be 1, because it's normalized. And you can easily check that it is so. And to do this, we can just use our nice identity with evolution operators, right? So you can write it like this. Use a cyclic property of trace to move this U here. So you have STS, which is 1 times rho S. So it's just trace of rho S. So it preserves, sometimes it's called TP, trace preserving. Second point, it preserves positivity, positivity of density matrix. Well, non-negativity, if you want to be very precise with your language. So again, if you take U, TS acted on rho S, now rho S is positive or non-negative, which means that it can be written as in this funny form I showed you before, as this product of square roots. And again, we can use our identity with evolution operators. ST. Okay, but this, if you notice, I can write as OS UST dagger times OS UST, which has the form of operator dagger times the same operator, right? Which is what you require from non-negative operators. So just to make it clear, I can write it like this, which is again non-negative. And the final thing to note about U is that U preserves purity density matrix. So this is kind of tricky. This is more tricky to describe what I mean by that. What I'm saying is like, if I take my US, acted on row as usual, and now row is, if row is mixed, right? I can write it in this form of mixture on projectors, or just use spectral decomposition to be more I don't know how to say it, more standard. So let's write down the spectral decomposition. Like that. And again, using the identity, we are like UTS. Sorry, I would use a little bit different notation here, because these are eigenvectors of density matrices time S. So let me just keep track of time. M YSM UST. Okay. So what happens here is eigenvalues don't change. It's just eigenvectors get evolved in time. So unitary map preserves eigenvalues. It just, let's say, rotate the eigenvectors, right? It goes from eigenvectors at time S and maps them to eigenvectors at time t. So in other words, if you have pure state, it will remain pure. If it was mixed, it will remain mixed to the same degree, okay? Unitary evolution operator cannot dynamically create mixed states out of pure states, or other way around, can purify states. So again, those properties wouldn't make any sense for evolution operators, because cats cannot be mixed, for example. They don't have trace, right? So those are extra properties that you get only for super operator evolution. So let me, I should finish right now, but let me jump to I will give you another assignment. So the code and another assignment I want to give you is 13. So find the interaction picture with respect to H0 of the unitary map for time-dependent Hamiltonian. So essentially, we had this disentanglement theorem, interaction picture, and stuff like that for unitary operator. Of course, it translates to analogous stuff for unitary maps. Okay, so just if you check the solution, everything's clarified, and you can just compare. And we should finish now. Fuck. Sorry. That's c'est la vie. That's what we have to do. Okay. I would jump to one more thing. Computability. Again, we have our unitary operators. We know how to compute them. Solve dynamical equation. What about computability of unitary maps? Well, we have dynamical equation, which you can integrate, of course, the same way. It's just The difference between unitary operators and unitary maps is just dimension, right? Because if your dimension is D, unitary evolution operators will be D by D matrices, right? And unitary maps will be D squared by D squared matrices. So exponentially larger. And this might be problematic. I mean, because you have exponentially larger dimension, so your matrix is also much bigger. So this might pose some problems. But it's not really a huge problem because UTS is, we have this favorite identity, right? Dagger, okay? So rather than attacking the full problem for unitary map, you can just solve this guy and just compute its dagger, and you have your curly U. So it's actually computability is the same problem as computability of evolution operators at this stage. So in other words, it's still simple, it's still easy. And now we have to finish. So then next week I wanted to talk about matrix representation for superoperators. Let me just flash it to you. I will talk about it in detail next week. So, operators are matrices. So you can write them as a table. Superoperators are also operators, also matrices. So there is a matrix representation for superoperators as well. There are bases, for ket spaces, vector spaces have bases, orthonormal bases, even if you have inner product. Well, we have vector space or Hilbert space of operators now where density matrix lives. You can have bases there as well. You have bases, you can define the matrices, matrix representation, and stuff like that. But details, I leave for next week. Unless you want to view it yourself in the script. Okay, so that would be all for today. See you next week.